Hello everyone. So this is the second part of energy conservation lecture. So we talk about mechanical energy, two types of mechanical energies. We talk about kinetic or kinetic energy. Use the shortened form KE for kinetic energy, and is given by half mv squared. This is the energy that a moving object has. If an object moves with a velocity v and has a mass m, we say that it accumulates kinetic energy, energy of motion, and it's given by half mv squared. And then we talk about potential energy. Which is given by PE, potential energy. This is due to its location, how far it's above the zero gravity level, and also it's due to deformation. So there's two ways that something can gain potential energy: by lifting it above some reference level, so we call that gravitational potential energy, which is given by mgh, mass times gravity times height from that reference level, and also elastic potential energy. This can have different ways of finding elastic potential energy based on what kind of object we are talking about. For an example, it could be stretching an elastic band or stretching a rubber band. So the more you stretch, it gains more potential energy. It accumulates energy to do work. It can pull things back. It could be stretching a bow. So when you pull the bow string, it bends the bow, it accumulates potential energy, and that energy can be transferred into the arrow and give it kinetic energy. The example we discussed was a spring, one of the simplest forms of elastic potential energy, an easy example, but very common in nature. And the equation is elastic potential energy for a spring is given by half kx squared. This x is the spring constant, k is the spring constant, x is the amount you stretch it or compress it. So we call these energies mechanical energies. And then we have this very important idea of conservation of energy. You might have heard about this concept. Energy can be neither created nor destroyed. So energy just transforms from one type to the other. So if you think about these two forms, kinetic and potential energies, let's say for an example, let's take an example like, say that we have some mass, couple of kilograms, and we lift it off of the ground, right? So for an example, here's the ground level, and the mass was over here, some m kilograms, and then you lift it up here. So mass is now here. So we raised it to a height of h meters. So it's h meters above. And if we take this as the zero potential energy level, now when you do the math, it's a good idea to mark where the zero potential energy level is. so that we know what's our reference point of measuring height. So you raise it to a height h. Now the potential energy up here, at this point, it has potential energy which is equals to mgh. There is no kinetic energy. If the object is not moving, it doesn't have any kinetic energy. Now if you let this go, if you drop it, if you release it, we know that it's going to accelerate downwards. We can use kinematic equations to find out how fast it's going to be. It's falling it's falling a distance of h. So by the time it reaches the ground, all that potential energy has become kinetic energy. So now the object, what it has is, if it is moving at a velocity v, what it has is kinetic energy at this point, which is equals to half mv squared. If you think about some place in between, like somewhere here, it still has some potential energy because it has some smaller height. So we can say mg little h. It has a little bit of potential energy, plus it's not that fast as it's over there, but it has some velocity, plus half k little v squared, right? So up here it's all potential. Kinetic energy was 0 because it wasn't moving. Somewhere in between, it has both potential and kinetic. Just before hitting the ground, just before reaching the 0 potential energy level, all it has is kinetic energy. Now potential energy is 0. Now the energy conservation says, energy conservation, it says, if there are no resistive forces, like if you are not losing energy on the way down, or if you are not losing energy in the system, right, there is air friction and all sort of resistive stuff. But if we disregard all that, if we consider an ideal situation, energy at any given point is going to be a constant. Means your starting energy, whatever you had at the very top, is the same at the very bottom or anywhere in between. Or you can say energy final should be equals to energy initial. Total energy, right? Not just any energy, but the total energy of the final system is equals to the total energy of the initial system. In other words, over here, now this is our final, this is our initial. Kinetic energy of the final system plus a potential energy of the final system is equals to kinetic energy of the initial system plus potential energy of the initial. The total kinetic and potential, the total of final is equals to the total of the initial. Or if we take any in-between point, that's also equal, energy at any point. This is called energy conservation. The total energy of a system remains the same. This is a very useful equation. This is a very useful concept. We can use this to find velocities at different places, or how high something can go, what will be the final speed if you drop something from a height. We can actually, energy conservation involves less math compared to using kinematic equations. You can of course still use the kinematic equations, but this is a different approach. This is another approach. Sometimes this can be much easier than working with kinematic equations. So let's take a look at few examples. Okay. Okay, so here we have an example. That is this mass m. Let's say this is 5 kilograms. We're gonna drop it from the height of so here's a building which is 50 meters tall. So you're gonna drop it from the top of the building, and you wanna know what's the velocity of this thing just before hitting the ground. Velocity over here. So we can do this using kinematic equations. So here's the old-fashioned approach, kinematics. If you do that, we have v initial 0, distance 50, acceleration 9.81. So we can do v final squared equals v initial squared plus 2ax, 0 plus 2 times 9.81 times 50. So we get 100, 981, that is v final squared. So v final is 981 square root, so something like 30 some meters, I believe. Let's see what it is exactly. Square root of 981, 31.32 meters per second. Okay. Alright, so now let's try the same thing using energy conservation. We're not going to use kinematics. We're going to solve the same thing. We're going to try to find the final velocity using energy conservation. Okay. So what do we do? Now up here, we know that the total energy, E total, is going to be all potential energy. Right? It's not moving, it's starting from rest. So therefore, what it has is the energy due to the height. It's all potential energy. Down here, it's going to be all. So E total is all kinetic energy. Because we take now here, we have to take this ground level. That's the best way to do it. The Earth's surface level, we take it as 0 potential energy level, right? Over here, potential energy 0. So the total energy going to be all kinetic. Potential will become 0. On the way down, when you release it, all that potential is going to convert into kinetic gradually. Somewhere here in the middle, over here, you'll have a combination of potential and kinetic. It's losing potential, it's gaining kinetic. So we can say, by using energy conservation, E total final is equals to E total initial. What is E total final? That's all kinetic energy. Is equals to initial, it's all potential energy. Or you can say this way. Hold on, let me erase this. You can say energy final, which is kinetic energy final plus potential energy final, equals kinetic energy initial plus potential energy initial. Kinetic energy final is half mv squared. Potential energy final 0. Kinetic energy initial 0. It wasn't moving initially, right at the top. Potential energy initial is mgh. Now we don't even need to plug any numbers as of now. You see that in kinematics we didn't use the mass. Even here, in many times, mass cancels out. You don't need to worry about that. Some cases you do, but in this particular example it cancels out. So zeros, they just vanish, they're not doing anything. you can divide both sides by mass, cancels out. We have half v squared equals gh. What we need is v, so we can write v equals 2gh. This half comes to this side, and then we take the square root to remove the square term, right? So we have v equals square root 2 times 9.81 times 50. Same thing like here, we get the same answer, 31.32 meters per second. Okay, so this is how we use energy conservation to find unknown speeds. Okay, all right, let's add something to this example. Let's say you want to find the speed when it is let's say 20 meters above the ground. When it is 20 meters above the ground, so here's the building again, 50 meters tall, you drop it from the top. When it is over here and moving over here, so this is 20 meters. What's the velocity? So what do? We define this as our energy initial. Now we take this as our energy final, and we write energy conservation. So initial energy, so we know that E final equals E initial. E final at this point, it has kinetic energy plus it has potential energy because it's still above the ground, equals energy initial kinetic plus PE. You don't have to write this all the time. I write it so that you see what I'm doing, right, where these numbers coming from. So kinetic energy final over here. So let's say the velocity it's moving down is v. This is what we're trying to find out. So that will be half mv squared. Potential energy. Now it's not zero. It is 20 meters above the zero level. This is our zero potential energy level, right? So that will be mg times 20, which is equals to kinetic energy initial up here, it's 0. Potential energy initial, it has mg times 50 meters. Now, so you see that again, even in this problem, you don't have to use the mass. It gets cancelled out on both sides. So we can divide the whole thing by m. So it goes away, and goes away. We have half v squared plus 20g equals 50g. So I'm going to take this 20 times gravity to the other side. So I have half v squared equals 50g minus 20g, which is 30g. Finally, I have v squared equals 2 times 30g. V equals 2 times 30 times 9.81 square root. So what's the answer? Square root of 60 times 9.81, 24.26. So you see, while it's when it is about 20 meters from the ground, it has this velocity. It hasn't reached the highest possible velocity, which is 31, which is just before hitting the ground. That's the highest. So somewhere before that you have somewhat less velocity. So if you measure it somewhere here, you'll have even less velocity with more potential energy. So likewise, on the way down, potential energy decreases, kinetic energy goes up, but the total remains the same. So those are the things to remember in these kind of problems. Okay. All right. So let's take a look at another example. Let me clear this. Here's another example. In this one, let's say that you're at an amusement park and here's a roller coaster. Here's a roller coaster track. So it starts up here. These are these coasters, and let's say it's, oops, this is the ground level. Let's say it starts up here, maybe like 40 meters above the ground, and let's say it starts from rest, so equals 0. When it reached the bottom, now it has gained a lot of velocity, all that potential energy up here, and if we assume that there is no friction along the tracks, all that potential energy will become kinetic energy down here. So that's the thing about energy conservation. Now if there is some friction, it will have little less kinetic energy. We'll have like, if energy total up here, but energy total over here will be little less compared to this, because friction is going to take some energy out. Otherwise it's going to be same. So you can again use energy conservation to find the speed at the bottom. Now think about it. We can't use kinematic equations in a situation like this. For an example, you have a car starting here and you want to find the velocity down here. This is not a free fall, it's not a straight ramp, it is more curved. So in these kind of situations, writing kinematic equations that's very difficult. You can, but it's going to be difficult. But when it comes to energy conservation, all you do is energy up here, E initial, make it equals to E final, and straight away you can find the final speed. All right, so there are so many advantages energy conservation theory has. Okay. All right. Let's think about another type of an example. This time, let's work with elastic potential energy. Let's say you have a projectile launcher. So here's the projectile launcher. Let's say we keep it horizontal. Right? This is horizontal, okay? It doesn't look like, but let's assume that it's horizontal. Okay, let me try again. Let's make it as horizontal as possible. So here's the projectile launcher, and this is the opening. We keep it horizontal, and here's the spring inside. Now what you do is you're gonna press this spring, you're gonna compress it, maybe to the first click or the second click or the third click, and then you have the, so once you do that, so it's gonna look like, oops, once you do that, okay, there you go, it's gonna look like this. It's compressed, and the plastic ball sitting in front of it. Let's say you compress a distance of x, this distance, and then when you pull the trigger, the spring has elastic potential energy, right? when you pull the trigger, all this elastic potential energy is going to push against this ball. It's going to accelerate the ball outwards. Now the spring is expanding, so that potential energy becomes kinetic energy of the ball. So by the time the spring comes back to its original size, all that potential energy has transferred into the kinetic energy of this thing, and it's going to move with some velocity v. So we can apply energy conservation again, assuming that there is no frictional forces between the spring and the gun barrel, or between the ball and the gun barrel. If we ignore all these little frictions, and mostly it's very little, all that initial potential energy now has become kinetic energy of the ball. So we can write energy conservation. So let's try this example. We have this projectile launcher, and the mass of the ball is, let's say, 100 grams, and let's say the spring constant is 250 newtons per meter. I'm just assuming some random numbers. And let's say you compress it, this distance, you compress it, x equals 6 centimeters. Now the question is, what is the speed of the ball when you release it? Now again, we can use kinematic equations. We can calculate how much force this spring is going to apply, which is a changing force, and the ball is accelerating distance x. This might not be a constant acceleration because the force applied is changing as the spring expanding. So energy conservation is much easier. So we're going to write energy conservation. We say that this is our energy initial. This is our initial system. The moment the plastic ball leaves the gun barrel, this is our final system. So we can say E final equals E initial. Now again, since everything's supposed to be a horizontal line, since everything's horizontal, we don't have to involve potential energy, because whatever we can say the system doesn't have any potential energy, or we can say whatever the potential energy it has remains the same. So it doesn't affect the calculations, right? Unless you tilt it, unless the height changes between initial and final. Like if you shoot it like this straight up, okay, so here's the compressed spring. This is the ball sitting inside. Initially, if this is the ground, initially it is at some height. When it leaves, it's at a different height. So there's height differences. So you have to talk about potential energy. But in this case, we don't have to involve gravitational potential energy. Okay, so going back to the problem. Energy final. We have kinetic energy final. This thing is moving, so we have KEF. The spring has some energy, so potential energy final is equals to KE initial plus potential energy initial. KE final, if it is moving with a speed v, half mv squared. Potential energy final. Now the potential energy, the elastic potential energy we are talking about, the spring has lost all its energy. By the time it comes back to the original length, all the potential energy has transferred into kinetic energy. So potential energy final is 0. Kinetic energy initial over here, this is our initial system, right? This thing wasn't moving, so it doesn't have any. Potential energy initial. Now for a spring, potential energy for a spring is given by half kx squared. We have the spring constant, we have the length, it's stretched, so we can plug those numbers. So half kx squared. Now you see it comes down to half mv squared equals half kx squared. Now here's a situation mass is important, it doesn't get cancelled out. So now we have to plug the numbers, we can actually get rid of the halves. So 100 grams is 0.1 kilograms, v squared equals 250 times, this is 6 centimeters, that is 0.06 meters squared. So v equals, we can do the math and figure it out, what's v is. Let's see, 250 multiply by 0.06 square root plus this divide by 0.1 square, this, that's 90, so square root of 90. .4 velocity it comes out is 9.48 meters per second. Okay, so energy conservation used is up. We applied that energy conservation principle to find this final speed. Okay, so let's think about another example. This time, let's say you have the projectile launcher, you're gonna shoot it straight up. So I'm just gonna draw the spring this time. So here's the spring inside, launcher is on the table. Now what you do is you're gonna compress this. So here's the spring uncompressed. Now you're gonna compress it. So this is the compressed one, and you place the ball here, and you're gonna release it. So when you release it, it's gonna push, you're gonna pull the trigger, it's gonna push back, so the spring is moving up, pushing the ball upwards. So by the time it comes back to its original length, that's when it's gonna lose the connection with the ball, means the ball is gonna start moving up. Okay, so how do we solve a problem like this? Now we can say this is the amount it was compressed, right? And then you release it. Now we can do the same thing. We can say something like spring constant is 250, mass of the ball is 100 grams. We use the same numbers. The amount you compress it, x equals 6 centimeters. Now you're going to keep it straight up. So the question is how high it's going to go, right? Max height. Now here's a problem. I want you to give it a try. Try to figure it out. You can use again energy conservation. So let's use energy conservation to figure this out. We can use kinematic equations also, but let's not do that this time. So you can define an initial and a final system. So we can take something like this as our E initial. When the spring is compressed and the ball just sitting on top of it without moving, so you know that there's a lot of potential energy, no kinetic energy, and you release it. So you need to define what's your final. For an example, if you want to find how high it goes, like let's say this is the highest point, maybe you can define this as E final. So up here, no kinetic, only potential. The other thing you need to think about is what is your zero potential energy level. If you take this as zero energy level, the table right, table surface, the ball will have some potential energy because it's above the ground. If you take this as zero potential energy level, where the spring stops when you compress it, then the ball won't have any potential. All the potential is due to this height, right, from here to here. So there are different ways of setting this problem up. So give it a try and see whether you can figure out the max height when you shoot it straight up. Alright, so that's an exercise for you guys. Okay, so let's think about another type of an example. So I'm gonna separate this. This time, let's say we again have a roller coaster problem. So it starts here, there's a drop, and then there's a climb, climbs like this. Okay, so let's say these two at the same level, this A and B are at the same level. This is ground level, C. Now the roller coaster cart starts here. Let's say this is 50 meters tall, and this roller coaster cart is let's say 500 kilograms. Now ideally, if there is no friction when you release it, let's say there is no motors or anything, it's just gonna move because of the potential energy it has because of this height, right? So when it reaches the bottom, all that potential will become kinetic energy, and you can figure out what's the speed. How do we do that? We can say let's say this is energy at A, energy at, let me call it B, and let me call this C, energy at B. So EB, total energy, is equals to EA. So because we take this as zero potential energy, all it has is kinetic energy. So that is half mv squared equals, up here it's starting from rest, so v is 0 here, so therefore all it has is potential energy, which is mgh. So again m cancels out, so we have v equals 2gh square root, which is 2 times 9.81 times 50 square root. I think we did an example with similar numbers, so 100 times, I think it's 31 point something meters per second, right? The velocity down here is going to be this. Now the roller coaster continues to go up. There is no friction, so ideally it should come to the same level without a problem. It should be able to reach point C, because this kinetic energy now is going to go up. While going up, it's losing kinetic energy, it's gaining potential energy. So by the time it reaches the same height, 50 meters, it should lose all that kinetic, and all that kinetic should convert into potential, so it should reach the same height of 50 meters. And again over here velocity will become 0. You can do the math starting with the total kinetic energy here and write another equation. You can say EC equals EB, so this will be mgh, this will be half mv squared. So do the math and find what's the height is. You see it's gonna rise to 50 meters. Now we're gonna make some changes. We're gonna say there is friction. The track has friction, right? So we're going to make some modifications. This track will have friction. because of friction, it's going to lose some energy. On the way down, it's losing energy. On the way up, it's losing energy. So as a result, let's say it goes only 30 meters up. It comes to this point. Oops. Comes to this point, and if you don't apply brake, it's going to roll backwards, right? So the maximum height it can climb is 30 meters. So the question is, what is the energy loss due to friction? Two, what is the thermal energy produced? Here's a new term. I want you to think about it. Okay, what is the energy loss due to friction? It climbs only 30 meters. What is the thermal energy produced? All right, two things. So I want you to work on this, and we can talk about this in class. Okay. Okay, so let me clear this whole thing. Now, finally, we have one more topic to discuss, which is related to work and energy. The term is power. I'm sure you are very familiar with this term. You have heard about this, and we use this all the time, right? But what is the meaning? What is the meaning of power in terms of physics, related to physics? Power is the rate at which work is done. Rate of work, or rate at which energy is produced or energy is spent. So rate of work is being done, or rate of energy is spent or produced, right? How fast, like how many joules were produced per second. So for an example, so let's see the units and all that. So power is denoted by capital letter P, and the unit for power is work divided by time, right? Rate of work is being done, so the amount of work divided by the time it took. So work divided by time, or we can say same thing, energy divided by time. We know that work and energy measured in what? Joules. Time, second. So this is joules per second. This is the unit. This is also called, this unit has a name, it's watts. And watts are indicated by W. Now there's a little, you can get into this confusion. Work is measured in joules but denoted by capital letter W. Power denoted by letter P, measured in joules per second, also called watts, right? So this W, the unit, is for watts. This W, this letter, is to indicate work. Power is work per second, or energy per second. Okay, joules per second. Traditionally, we use, people use, there's this traditional unit which is horsepower, right? You know, that animal with 4 legs which can run really fast. Horsepower. It's an old-fashioned unit, but still widely used, especially when it comes to vehicle engines. Like you compare, like, you know, sports cars or muscle cars, so many horsepowers, stuff like that. So 1 HP is equals to 746 watts. How many joules it can produce per second? That's the idea of power. That's the idea of horsepower. How much energy produced per second? So if somebody says their car has an engine of let's say a V6, maybe starting with 300 HP. Now you know how many joules it can produce per second, so you can have an idea how much work it can do per second, right? So we'll get into details in a little bit. Okay, so that's the idea of power. Okay, so let's try an example related to energy and power. Let's say there's a set of steps that somebody wants to climb. So we have a jogger. He's running up for exercise. He's 60 kilograms, and the vertical height of these steps, this is going to be, let's say, 5 meters, the vertical height. So he's gonna run up the steps, right? So question number 1, he's going up. So at the end he will be over here. So question number 1, the amount of work or energy required. So let's try that. How much energy does he need? Now to go up, to find the energy, let's calculate the work we need. Work needed to be done. Now we know that if we calculate the work, that gives us the amount of energy he needs to spend, right? So we'll calculate the work. How do you find the work? He's going in this direction, so we can get this, it's like we can assume it as a ramp, and here we have this mg sine theta, and then we have to apply an equal force to go up, and then we can multiply that force by the distance he goes. You can figure out how much work he does. But here we don't have that information. All we have is the net height. The starting point is here, this is the final point. We can find the work the same way, assuming that he's going up straight. He's using the steps because it makes it's easier to do it that way, but the amount of energy he has to spend theoretically or technically gonna be the same as climbing straight up. So if you do that, you have the body weight mg, you have to apply an equal amount of force and multiply that force by 5 meters. So the work will be force times distance, which is mg times distance, which is 60 times 9.81 times 5. So what do we have? 300 times 9.81, which is 2943 joules. He needs to spend 2943 joules. Okay, so we can think of this in a little different way. We're trying to find the work needed or the energy he needs to spend. Let's think about energy conservation. Energy conservation. Well, not really energy conservation. Let's just say just energy. How much energy you need? He was initially here. Now he's up here. How much potential energy has he gained? Like, what is his potential energy up here? So potential energy at the top is equals to mgh, 60 times 9.81 times h, which is 5. So relative to the ground, this is our 0 level, right? Relative to this ground, now his potential energy is this number, which is 2943 joules. Now he gains 2943 joules when he reaches up. That means that's the amount of energy he has to spend. So the energy required, we can do it in both ways, comes to 2943 joules. Now the next question. Now this is the amount of energy he has to spend. The idea of power is, what is the power requirement? It depends on how fast he wants to do this. He can climb the steps in 10 seconds, he can do it in 5 seconds, or he can do it in 20 seconds. So depending on how fast he wants to do it, the power requirement going to be different. If he's a powerful person, that's the idea, we say like a powerful vehicle, or if he's a powerful person, he can do it fast. He can spend this energy quickly. So let's say reach the top in 10 seconds. So what's the power requirement? Power is work divided by time, or energy divided by time. So 2943 joules divided by 10 seconds, which is 294.3 joules per second, or watts. He need to have a power output of 294 or 300 watts in order to do this in 10 seconds. Let's say he wants to get there in 5 seconds. So now the power requirement is same amount of work, right? The starting point and end point difference, it's going to be the same. That's the amount of energy you have to spend, but faster. So the power requirement is half of 294. So let's see, 2943 divided by 5. Need to do it faster. So 588.6 joules per second. So if you want to do it faster, you need to spend energy faster, more energy within 1 second, right? So that's the idea of power. Okay, so let's see what else we have. Alright, so that's kind of the lecture I was planning to discuss with you guys. So go over this, think about kinetic and potential energies and how energy conservation works. The total remains the same, and when there is non-conservative forces. Now friction is something like that. Friction is a non-conservative force. If there is friction, you can't recover the energy you lose against it, right? If there is no friction, you start with potential at a height, you have the same amount of energy as kinetic energy at the bottom. So those are conservative forces, right? You don't lose anything, even though your path changes. Like for an example, here, like in this case, this jogger's case, he can take this route to go to the top. So this is the starting point, so he's here. Or he can take a route like this, or he can take a route like this. As long as there is no friction, if the starting point and the end point is going to be same, the amount of work you need to do, it's going to be same. It does not depend on the path, right? He can even climb straight up like this, same amount of energy. But if there is friction, a non-conservative force, it won't be the same, right? Then the amount of work you need to do will depend on the path you are taking. So that's something to think about. We will work on few examples in class. Okay, So, all right, thank you all.